Let's take a look at some different types of chemical reactions. So when molecules or when atoms react with one another, then new bonds are formed, old ones are broken. And here are some definitions that are something that you need to know. When a reaction is endergonic, that means you need to put energy into the system. That means this system has absorbed energy and the products have more energy than the initial reactants. When a reaction is exergonic, exo for out means the energy is being released. So then the products are having less energy than the compounds that you put into the reaction, so the starting compounds. Okay, let's take a look at a synthesis reaction. So those occur when atoms, ions, or molecules combine to form new or larger molecules. So here, the idea here is that you have compound A, which could be a molecule or an atom, plus compound B, which could be an atom, ion, or molecule. We're combining A and B to form the product AB. So that's a synthesis reaction. Another definition that you need to know is anabolism, and that is a lot of times what happens in cells when you're making macromolecules. So if you're combining amino acids to make proteins, that's an anabolic type of reaction because we're building higher energy molecules. And so those are synthesis reactions in the cell that were then the overall reaction. Just to remind you of the previous terms, this would be an endergonic reaction because it absorbs energy and the resulting molecules have more energy than the starting compounds. Opposite to this would be decomposition reaction, and there you're breaking down molecule AB into subcomponents A and B. So now the products are separate here. A and B are separated. They have been decomposed from the original AB, and that is typical kind of a catabolic reaction where energy is being released, and the products here, A and B, they have less energy than the starting compound AB. Okay, exchange reactions. Here we have an example: sodium hydroxide plus hydrochloric acid, so NaOH plus hydrochloric acid. They form salt, NaCl, plus water. So that's a base plus an acid forming salt and water, the typical type of exchange reaction. In living systems, a lot of reactions are reversible. And so what you see a lot of times is depending on the availability of A and B or AB, we're pushing the reaction in either direction. If we have a lot of A and a lot of B, and not much AB, and we have some heat available, we're going to push the reaction in this direction. If we have a lot of AB and we have, let's say, a lot of water, then we may decompose AB back to A plus B, and we're pushing the reaction in that direction. So that means this is a reversible reaction. Important biological molecules, we're going to have a whole section later talking about important biological compounds. We define something as organic compound when it contains carbon and hydrogen. A lot of times there's also some oxygen involved and some nitrogen, but by definition you must have carbon and hydrogen to classify something as an organic compound. Inorganic compounds, they typically lack carbon. They're just quite different. A lot of times they're small and fairly simple, but that's sort of just on average. You might wonder about something like CO2. So based on this definition, CO2, carbon dioxide, does not qualify as an organic compound because it doesn't have any hydrogen. So it would be technically an inorganic compound, even though it does have carbon inside of it. Okay, now let's talk a little bit about water, because biological systems on planet Earth are water-based. Water has neither it doesn't have any carbon, and so it's definitely not an organic molecule. It is inorganic. It is a polar molecule, and that's very important. That's that uneven sharing of a pair of electrons that we talked about earlier. So we have this unequal distribution of these pairs of electrons, which creates this polarity in the molecule where the oxygen end is slightly negative and the hydrogen end of the molecule is slightly positive. And then these water molecules attract one another, creating hydrogen bonds, and that creates the unique properties of water. Water is a great solvent, and that is because all these ionic substances, they like to form hydration shells. Anything that also has polarity likes to mix with water, which is most organic compounds. And so we have water as a great solvent. Also, the hydrogen bonds, they absorb heat, and that makes a temperature buffer, and so that gives water these unique properties. You know that if you live close to the ocean, then the temperature fluctuations are not that big. If you live out in the desert and the nights are cold and the daytimes are super hot, but if you live close to the ocean, the presence of a large body of water, it just really has this high specific heat, and it absorbs a lot of these temperature changes. It's a temperature buffer. Anyway, so here's a water molecule again. Nice and big. The H2O, water. We have 2 hydrogens, 1 oxygen, and although water does not carry a charge, you do see a minus up here and 2 pluses up here. They are, let me remind you, they are not charges, but they refer to the polarity, because there are 2 electrons, a pair of shared electrons sitting right here and right here. And I'm going to draw them closer to the oxygen end rather than the hydrogen end. They're not in the middle, so we don't have an even sharing of that pair of electrons. Oxygen is kind of greedy, and it's bigger and stronger than hydrogen, so it wants to pull this pair of electrons closer to itself, but it can't quite succeed. And so it pulls these electrons closer to the oxygen end, and therefore we get the slight negativity, and hydrogen's barely hanging in there, holding on to that pair of electrons, but it can, and so it has a little bit of a positivity to it. So that creates this polar the polar covalent bond here, and due to the polarity in the molecule of water, we end up with hydrogen bonding. Hydrogen bonding is this weak attractive force. This dotted line right here, it is a bond, but it's a weak bond, and it can be easily broken. All you have to do is heat up water, and these water molecules, they will go their separate ways. But at room temperature, these hydrogen bonds, they make it so that water is a liquid at room temperature, which other molecules of that size are long a gas at that temperature. So hydrogen bonding does a good job in holding these water molecules together in a bucket of water. Also, here are the hydration shells that I mentioned earlier. So here you see sodium chloride crystal, salt crystal. And now you all know that you can dissolve salt in water. So what happens when you're dissolving salt in water, then the sodium ions, they are surrounding themselves with the oxygen end of all these water molecules. You see these water molecules? And here the chloride ion with its negative charge. There's the chloride ion, the Cl minus. That one surrounds itself with the slight positive end of these water molecules, so the hydrogen end of the water molecules, and we call those hydration shells, and that's what makes it possible for salt to completely dissolve in water. It likes to do that. Now we're gonna move on to acids, bases, and salts. Okay, so here we have a very strong acid, hydrochloric acid, HCl. And HCl also likes to dissociate into hydrogen ions, H plus and Cl minus. And so there we have this same scenario as with a salt. We are dissociating the substance HCl into a hydrogen ion and then a chloride ion, a positive and a negative ion. So what happens if I put hydrochloric acid into water? So what's going to happen is that the HCl is going to dissociate into H plus, the hydrogen ion, and the chloride ion. Now the pH is the measure of how many of these guys do I have. And because we're spanning 14 orders of magnitude, we're going to take a log scale approach to this. So we have 14 orders of magnitude to deal with, and therefore we're going to take the negative logarithm of the hydrogen ion concentration, and that's our pH. So a substance that absorbs hydrogen ions, such as sodium hydroxide, that would be classified as a base. And so here we have this hydroxide ion, the OH minus, and it loves to go out for seeking out for hydrogen ions, the H pluses, and wants to add it to make water. And so this is a strong base. It wants to absorb hydrogen ions where it can find it. And so therefore we call that a base, or something that reduces the number of hydrogen ions that are available in a solution. Okay, so if you're putting NaOH into a bucket of water, then you have the sodium ion again here, but you have the hydroxyl ion, the OH minus, and that one absorbs every last hydrogen ion it can find. So the concentration of hydrogen ions in this beaker here will be very low. So that means the pH is going to be very high, and I'm going to show you how that works in just a sec. So here, one more reaction before we get to the pH. Here we have a salt, sodium chloride. We already know this. So in this case, we're dissociating to two ions, the sodium ion and the chloride ion, but neither one of them is a hydrogen ion or hydroxyl ion, so it doesn't really change the pH by either adding or withdrawing hydrogen ions into a solution. But if you are reacting an acid plus a base, if you react them with one another, then you'll produce salt and water. So here the salt dissolved in water, forming these hydration shells. We have a sodium chloride breaking up into a sodium ion and a chloride ion. That's a typical salt, but it doesn't affect the hydrogen ion or the hydroxyl ion concentration. Now here, the concept of pH, and if you like math, you're gonna love this. If you don't like math, I'll offer you I'll give you some hints on how you can make this as pain-free as possible. But for those of you who like the math, which includes me, happens to be, I like math, the pH, the P comes from the logarithm, from the Latin word for potentia, which means the logarithm. So it's the exponent of the hydrogen ion concentration. And so basically the idea is this. If I have a solution where 1 in 100 molecules is a hydrogen ion, so 1 over 100, 1 in 100 molecules is a hydrogen ion. That means if I write this as an exponent, that is equal to 10 to the minus 2, if I write it as with an exponent, right? So 100th is equal to 10 to the negative 2. Now this negative 2, this concentration of hydrogen ions then expresses a pH, where pH is the minus logarithm to the base 10 of the hydrogen ion concentration. So that means a solution that where 1 in 100 molecules is a hydrogen ion has a pH of 2. So the logarithm to the base 10 of 100th is minus 2, and the pH is the negative logarithm, so it's 2. Okay, now let me show you why low pH numbers mean that the acid is very strong. Let's say we have a solution where only 1 in 1,000 molecules is a hydrogen ion. So 1 in 1,000. And that is expressed with an exponent as 10 to the minus 3. So clearly, a 1 in 100 is much stronger, it's 10 times stronger than 1 in 1,000 being a hydrogen ion. So if I now take a look at the exponents, my exponent here is minus 3, my pH is the negative exponent, so the negative of negative 3 is plus 3, so the pH here is 3 of the solution. Do you see how a pH 3 is weaker than a pH of 2? Let's use one more example. Let's say 1 in 100,000 is 1 out of 100,000 molecules in a bucket of water is a hydrogen ion. So now we have, as an exponent, we're going to write this as 10 to the minus 5, 1 in 100,000. Clearly, 1 in 100,000 is much less of a concentration than 1 in 100 or 1 in 1,000. So now our negative exponent here is minus 5. The negative of minus 5 is plus 5. Our pH is 5. So clearly, a pH 5 solution is less strong, has fewer hydrogen ions as opposed to a pH 3 or a pH 2 solution. Okay, so that's the explanation of how these numbers come about. For those of you who like math, you can also plug this into this. You can calculate the pH. It's actually not that difficult. All you need to know is the hydrogen ion concentration, and you take the negative logarithm of the hydrogen ion concentration, you're good. So, but here, for those of you who don't like the math, I'll give you some ideas of how you should study this. Just one last point here. Most organisms grow best between a pH of 6.5 and 8.5, and you will see that's near the point of neutrality. We'll take a look at that. In fact, you can take strong acids to discourage the growth of most microorganisms. So here is our awesome pH scale right here. So the pH scale is a scale that spans 14 orders of magnitude, and as you just saw, the pH number refers to the negative logarithm of the hydrogen ion concentration. Now, for those of you who don't like logarithms, don't really like math at all, here's the deal. You need to know that the point of neutrality is 7. So you need to know that the pH scale is a scale that goes from 0 to 14. The point of neutrality is 7. Any pH number that's less than 7 is getting increasingly acidic. The smaller the pH number, the stronger the acid. Any pH number that's larger than 7 is a base. The higher the number gets, the stronger the base. So the strongest base is pH 14. The strongest acid is a pH of 0. So that's my lifeline for those of you who don't like the math and don't like to think about negative logarithms, or it gives you anxiety if you just think about a logarithm. So here's what you really need to know. So you need to know the pH scale is a scale from 0 to 14, and the point of neutrality is 7, which is where most forms of life like to grow in this range here, sort of the 6 to 8. So that's sort of the most popular range, right around the point of neutrality. That's where most organisms grow best. And we're going to continue our discussion with some more organic chemistry in the next section.